For this example, we're going to look at a 3D object. It's this piping system with a loading of F of 200 pounds and P of 50 pounds. And we're supposed to determine the internal forces acting at section C. So we're going to look at this section C. And if I cut this, right, I'm going to have my loadings all at this point here, and I'll have one free body diagram down here of this, and then my other side I will have this part here with my piping going this way. So the question is, which side of the piping do I want to look at? Do I want to look at this section here or this lower end of it? After I put all the loads on it. Well, to make life easier for us, if I look at just this section here, I don't have to worry and solve for our reaction forces at O. So I'm going to draw the free body diagram of this lower section so I don't have to calculate all of those moments and forces in the X, Y, and Z direction at O. Sometimes you may have to do that, though. Okay, so I drew the free body diagram for our cut using the end section of this. And if we look at it, we have, of course, our weights that are on here. We have our dimensions that are on here. We have our coordinate system. And the most important part that we've added is our internal loading. We have our normal, which is coming right off or perpendicular to our cut, NC. I have our moment around the axis, that y-axis, so that's MCY. I have a shear force in the Z direction and X direction, and I have bending moments around the x-axis and the z-axis at point C. So once we've drawn our free body diagram, we go through our same steps that we've done throughout the whole semester, and that is really solving for our forces using the equations of equilibrium. And if I look at this, I can easily solve for our forces in the x direction. And all I have is this shear force VCX. So VCX equals 0 pounds for us. Next, I'm going to sum forces in the y direction. And I have a positive NC, a minus 200 pounds. That tells me NC is in tension with 200 pounds. Next, I can sum forces in the z direction. And if I do that, I have VCZ and plus 50 pounds, or VCZ equals a negative 50 pounds. Notice that my shear forces are not in tension or compression. They're running along that surface, so there's not such a thing as tension or compression along for a shear force. Okay, all that I have remaining now is to solve for my moments. And I'm going to look to see if I can solve for this MCY, which is this twisting action around the shaft itself. If I look at it, this 200-pound force does not cause a twisting action around that. It is parallel to that axis, that y-axis at that location. And this 50-pound force is right at that same axis if I brought it down. So it doesn't cause any moment around that. So if I look at this and I sum moments at C around the y-axis equals 0, all I have is MCY. So therefore, MCY equals 0. So there is no twisting action around it. Next, I'm going to look at my moment around the x-axis. Again, this 200-pound force does not cause a moment around that axis, around the x-axis itself. But my 50-pound force does cause a moment around that x-axis, right? It wants to bring it up around this direction, around this x-axis at point at C. So if I sum moments at C in the x direction, should equal 0. I have a positive mcx, which is my internal moment, bending moment, and then I have a negative 50 pounds times 12 inches. That gives me mcx is equal to 600 inch-pounds. And that's a bending moment. It's trying to bend that. Okay, last is I need to analyze this mcz. So the moment around the z-axis, we see that this 50-pound force does not cause a moment around. They are parallel to each other, so that is not going to cause a moment. But this 200-pound force will cause a moment around the z-axis. So if I write out my moment equation for that, see if I can get enough room in here. Summing my moments, mcz equals 0. mcz is my moment that I have up at the cut itself, my internal bending moment, minus, it's a negative moment, this is bringing around, is a negative moment of 200 pounds times the moment arm of 18 inches. That gives me mcz is equal to 3,600 inch-pounds. These types of problems are very important. You should understand how to find these. They come into play a lot in mechanics of materials and analyzing complex structures.